Video, we are going to prove the mean and variance of the Poisson distribution. Okay, we have the probability mass function of the Poisson distribution defined as P of x. The probability mass function of this distribution is in the form of e to the power minus lambda, lambda to the power x divided by x factorial for the values of x ranges from 0, 1, 2 and so on up to infinity 0 otherwise, and this lambda is the parameter of Poisson distribution is non-negative constant. For the mean or the mathematical expectation of this Poisson distribution, we have the formula as expected value of the random variable x is equal to summation x times px. This is the formula of mathematical expectation, or simply the arithmetic mean of the random variable having the probability mass function px. For the Poisson distribution, we have this probability mass function. After substituting the value of this px in this equation, we get the expression this: the value of x range from 0 to infinity x times the second part is the value of the probability mass function. For simple calculation, we have to cancel this variable x with this x factorial. So we have to expand the x factorial as expected value of x is equal to, this time here the factorial of x is break down to the two term x in time the x minus 1 factorial, and we can cancel this the value of x in numerator and denominator. It produces the expression as we have x minus 1 factorial in the denominator. To make harmonize, we make this lambda as lambda to the power x minus 1. This negative lambda to the power minus 1 is balanced by lambda to the power plus 1, and this term e to the power minus lambda is independent of x, so goes to outside of the summation sign, and this summation is expressed as when x is equal to 1. This is lambda to the power 1 minus 1, lambda to the power 0, 1, lambda by 1 factorial, lambda square by 2 factorial, lambda 3 by 3 factorial, and so on. The important point is that the summation sign here is x is equal to 1 to infinity, and in the first step the summation is x is equal to 0 to infinity. The reason is the first term is cancel out, or when x is equal to 0, x minus 1 factorial become minus infinity, and if the denominator term is infinity, then the first term becomes 0. So our summation ranges from x is equal to 1 to infinity, and this expression is the expansion of this term e to the power lambda, and if we expand e to the power lambda, this is the series. So e to the power minus lambda and e to the power plus lambda is cancel out and remain lambda. Therefore the mean or the mathematical expectation of this Poisson distribution is equal to lambda. Therefore lambda is the parameter of Poisson distribution, also the mean of the Poisson distribution, and it is used to compute the probability distribution of this Poisson distribution. For variance of the Poisson distribution is defined as variance of x is, we have the excellent expression, the variance is expected value of square of the random variable minus time square of the expected value of random variable. This is the definition and expression of variance of any distributed random variable. In case of Poisson distribution, we have the expression, the expected value of square of random variable is x square times px summation from 0 to infinity minus the expected value of x is lambda. We have already proved, so it is lambda square. For this calculation of this first expression, we have to break down the x square term into two terms. X multiplied by x minus 1 plus x, it becomes x square minus x plus x, minus x and plus x is cancelled out and it is equal to x square, and it produces the two term. The first term multiplied by px plus second term x times px. This second term is expected value of lambda. The expected value of Poisson distribution, and the value of this is lambda, and we have to calculate the expression of this term as after substituting the value of px from the Poisson distribution. The motive behind the simplification of this term is that we have x factorial, and x factorial produce the term x multiplied by x minus 1 factorial, x minus 2 and so on. So to cancel this term, we break the x square term into these two term. This is the one key point while you have to remember while prove the variance of the Poisson distribution. And this term is the mean itself. This lambda square is the square of the expected value, and as usual manner we expand x factorial. X factorial is expanded here into x minus 1 and x minus 2 factorial, and these two terms are cancelled out. And by observing this x minus 2 factorial in the denominator, we make this lambda to the power x as lambda to the power x minus 2, and this minus 2 is balanced by lambda square. As earlier in the mean, e to the power minus lambda is independent of summation, so outside the summation side, and these two terms remain same. After substituting the value of x is equal to 2 to infinity, here also these two terms are cancelled out. The value of x ranges from 2 to infinity, or when x is equal to 0 and 1, x minus 2 factorial minus 1 factorial lead to infinity, and 1 by infinity then becomes 0. So the value of ranges is from 2 to infinity, and this expression is the expansion of e to the power lambda. So e to the power lambda and e to the power minus lambda is cancel out. E to the power produce e to the power 0, and e to the power 0 is equal to 1, and this lambda square and this lambda square cancel out, and finally the variance of the Poisson distribution is also lambda. In conclusion, we have the mean, that is the mathematical expectation of this Poisson distribution, and the variance is equal, and that is the lambda, which is the parameter of the Poisson distribution.